So I would like to dedicate this talk to my colleague Eugène Kremer, who died last year, and with whom I did this fascinating and very exciting discovery of E8 in, if not physics, theoretical physics. So it was discovered actually in 78, 79. And I want to, the reason my work is being done now is that I can still not understand from first principles why E8 occurs, why these U dualities are as magic or as exceptional as they are. And I want to understand that better. So the philosophy will be to try to look for occurrences of E8, decompose each case and analyze each case separately, put some classification, and then try to understand. So in fact, the way E8 was discovered was by this stupid addition, 128, which is the number of scalar fields, plus 120, which is a dimension of R symmetry, is 248. So bosonic action was constructed shortly thereafter. E7 was actually the first to be constructed. That was our goal in 4 dimensions. But in the 1979 paper, we had also E8. So in view of time, and because I wasted a lot, if you don't complain, I will assume that you know about Cartan maximal abelian subalgebra, root lattice, Cartan matrix, Nikken diagram, and affine extension. Affine extension was actually mentioned by Fring in his talk, and nobody complained. So I think maybe I will just insist on one thing. The Nikken diagram is the way to present a Lie algebra with generators and relations starting from various SU2 or SL2R factors. And D4 consists of 4 of these. And these are the 4 vertices of this Y picture in red. And the line tells you exactly how the 2 SL2 or SU2 factors combine to make a larger group, and how do you construct the full SO8. Now the affine SO8 makes an X. It has one more SU2 factor. The rank is one more, and we'll come back to that later. So let me start with 2 other much modern, a little bit more modern instances of E8 in physics. The first one is not so modern, but it's 10 years after maximal supergravity. AB Zamolodchikov discovered that the Cartan matrix of E8, the exceptional Lie algebra E8, and the spectrum of masses of an integrable deformation of the critical Ising model, Ising field theory in the magnetic field. In fact, in detail, it's the components of its Perron-Frobenius vector are actually the same. So it's actually a field theory, but it comes from a discrete lattice theory, which is called the dilute A3 statistical model, if you're interested. So this is an instance of what I want to do. He discovered E8. And then the next question is E8 coming alone, or does he have friends or brothers and sisters who arise and occur in the same situation? In this case of Zamolodchikov, the family of E8 is replacing Ising by pods. In fact, there's also extension to superalgebras. And that's a family I will describe later, and I will call it the green family. In fact, I will use the color code because it's a bit complicated. The biggest, most frequent families are green and blue, and there are red, which is not so well understood. It's more stochastic, not as family prone. Our family is too small. And there are also the Pain-Levé case, which will be orange, which is a little bit also mixture of everything. The second case, which is very recent, is that there was a recent proof 3 years ago, by Wiazowska, that the E8 root lattice, which has been known for some time to be the densest three-packing in eight-dimensional Euclidean space, was actually the densest possible three-packing, not only lattice packing, in these 8 dimensions. And then this result was extended to 24 dimension. The Leech lattice was proved to be also the densest packing, not only lattice. And it makes a family now of dimension 1, 2, 3, 8, and 24, which is not complete, but it's in red because it's a bit stochastic. 8 and 24 are okay, but 1, 2, 3 together with 8, 24 is not so usual. For instance, E7 is known to be the densest lattice among lattices, but it's not known to be densest among packings. So I repeat once again, the problem of today will be to encounter E8 and then to find a family of E8. So I'm sorry, this is not exactly appropriate to a conference because E8 will be the part, and it will belong to several totals. So usually it's several parts in one total. Here it's the opposite, but it's kind of similar. So I suppose nobody will complain too much. So some other example of sporadic or sparse E8 families are given by even unimodular lattices. You know, they exist for dimension multiple of 8. So E8, E8 cross E8, SP32 over Z2, which is very familiar to string theorists, Lisch lattice, Niemeyer lattices. Modular forms also are related to these 24 and 8. And also for to E81, there's an identity which was used in Kac-Moody theory and Moonshine, which relates the J invariant of complex function theory to the cube of the partition function of the E8 affine Lie algebra. So red will be somehow related to number theory, modular invariance, and things like this. But it's, I put a question mark. Then let's go back to what is very well known, but not so interesting. Well, you know, you can classify Lie algebras, simple Lie algebras, and among them, you can classify the simply laced ones and ADE. So the ADE prime is a typical example of what I want to do, because what I want to do is to get a family, many occurrences of the same phenomenon. And among these, you can identify the exceptional ones, E8076 F4G2, and the simply less exceptional ones, E8076. So these are the smallest building blocks, if you wish, of the families I'm going to construct, but they don't really apply in the first case. So then there will be three big instances of families. In fact, there will not be line families, one-dimensional families, but two-dimensional ones. The first one, which is very old, is Freudenthal-Tits magic square, which is two-dimensional. I will show it at the end of my talk. E8076 F4, D4, G2, A2, A1, and the trivial Lie algebra or group. This is what's called the group, what I call the green family, which is due to Cvitanovich and was clarified and developed by Deligny and Gross. So it's another, it's a triangle, as I will show you. So this is one side of the triangle. And it's to be distinguished. For some time, Cvitanovich and myself were arguing that we were discussing about respectively the same or not the same family. I think they're definitely not the same. They are even of different natures. And the family of U-dualities is also well known to string theorists, at least, is E8076, D4, D5, sorry, A4, A2 cross A1, R cross A1, because these are real forms, R or A1, depending of type 2A or type 2B, and the trivial one for M theory. These were constructed, triangles were constructed by myself and expanding on the work with Sartre to Eugène. And then the last family would be Pain-Levé. So if you look at ordinary differential equations, it was mentioned by Marquette that this is actually, it stops with Pain-Levé 6. But if you look at this Lie algebra structure I want to exhibit, there is more than 6. Yeah, there are all these slots here. So there is E8 and D8 in rank 8, E7 and D7 in rank 7, E6 and D6. So that's already 6 plus 2, that's 8. D5 and D4 are the well-known ones. So the usual Pain-Levé are E8, E7, E6, D5, and D4. I will explain what these mean. And the Pain-Levé come with a pair of Lie algebras, not one. And then, in fact, dual, which is, so E8 is dual to 0, and D4 is dual to itself. This duality is very similar to the duality in this case of Cvitanovich-Deligny family, where you are looking at a maximal, a commuting pair or maximally commuting pair inside E8. I will come back also to that. Sorry. Then let me emphasize a rather trivial thing you may have encountered in your career or life. these so-called triangle groups. Yes?
5 minutes left.
Yes, thank you.
Yeah.
And the first one is a triangle group is called TPQR. P refers to the length of the branch or the arm or the leg of this diagram. So here each leg is 2. So this 2, 2, 2. For D41, the legs are 4, but I will use PI to show you why it's useful. Next slide. The next slide shows this. The classification of finite or affine is usually done on triangle diagrams by the difference between 1 over P plus 1 over Q plus 1 over R is strictly larger than 1 or equal to 1. I claim that if you want to see D4 as exceptional, like E8 and so on, you want to change this condition to the following one: sum of pi minus 1 over pi, where pi are integers, but now the number of indices of pi is arbitrary, is equal to 2. I call it the equation star. And D41 is indeed solution with 1/2, and it corresponds to pi's are again the length of the arms. So I don't have time to comment on the connection with Riemann-Hurwitz and Riemann-Roch formula. So as I said, D41 is as exceptional as E affine in a sense. I also want to say, as there is a one-to-one correspondence between simple algebras, finite simple algebras, and the affine extension, to say that E8 is exceptional is almost the same as saying that E81 is exceptional, but D41 is exceptional where D4 is not. So AD extension is just to say that we'll just keep that, sorry. Now, let me share with you an exciting remark. This equation star, which I just showed you before, this one here, has been actually discovered in a little bit generalized form by 2 students of Cauchy. So that was very long ago in 1887. And I claim that, sorry, 1856, that is 31 years before Killing discovered E8 and 112 years before Kasmoudi discovered affine Kasmoudi algebras. And they show that they were actually studying first-order differential equations, contrary to Painlevé equations, which are actually second-order, but with the Painlevé property. It's well known that they are actually just a Riccati equation and Weierstrass equation, but they looked at this special form here, and they found that actually the solution corresponds to some exponents of some pi's which are here. And if you look at those, I was a little bit fast for the e's, but these are precisely D41, E61, E71, and E81 are fine. And this each time pi minus 1 over pi. So they found, and they have exactly these numbers. You have to play a little bit with the definitions to get exactly those, but they are in the classification. And this corresponds to something that will be important to get the Painlevé equation, which is what I said here, because as Marquette explained, Painlevé, Fuchs, and Gambier found 50 solutions of Painlevé property equations. Only 6 of them were transcendental or non-trivial. But in fact, if you look at the way to derive these 50 solutions, this work of Briot and Bouquet is used every step of the way. So there's a connection between the D4 of Briot and Bouquet and the D4 of Painlevé, that's for sure. So how am I doing? Yeah, sorry. I skip that. So in Painlevé, again, there's one symmetry which is called the Becquerel symmetry of the Painlevé equation, and the second one, which is related to the initial conditions or holonomy of the set of basis of solutions of Painlevé. And this pair is actually a commuting pair in E8. So the blue family is similar but not equal to the green. So let me show you exactly what I mean. So let me recall first the magic triangle. E8, E7, E6, and F4. So F4 is not simply laced. I obtain in a uniform way in this square by choosing a division algebra. Here you have the octonions, here you have real numbers. So division algebras over the real numbers. Here you take twice octanon algebras, and by a uniform construction, symmetric or non-symmetric, there are several ways. you get E8 Lie algebra that was done by Titz. And there are, since then, other constructions by Winberg, and recently there was more work by the British group. I apologize. So I want to emphasize that F4 and C3 are not simply laced, so they cannot appear in diagrams where I will only have ADE groups. So the next one is precisely a diagram with LAO, non-simply laced groups. This is so-called Cvitanovich-Gross-Deligne. It corresponds to an analysis of invariant theory. And invariant theory doesn't care so much about simply laced or not simply laced. To give you a feeling for that, SO2n and SO2n plus 1, you cannot see the difference if you don't go very deep in representation theory of spinors, or maybe it's the same if you go into root theory. So let me pose a challenge to each of you. Can you please give me a way to describe, to differentiate simply laced and non-simply laced Lie algebras without mentioning roots? And I cannot do it. So if you can do it, please tell me. So this construction is this green family. The motivation for this is not so clear in the work of Ross and Deligne. In the work of Cvitanovich, it corresponds to defining this Lie algebra by a very well-defined set of fundamental representations with well-defined invariants. And the same here. And to get the rest of the triangle, you do some kind of strand construction of the commutant of one of the algebra with the other one. And you can easily see that this is a symmetric construction. So this A1 minus 3 is the same as this A1 minus 3. And this gives a triangle, because otherwise it doesn't work. And let me finish with this, maybe the best known, almost best known triangle, which corresponds to supergravity, or not quite supergravity, maximal supergravities, but an extension we have discovered with Kremer, Liu, and Poe in this preprint, which never bothered to publish, but it's correct. And it corresponds to starting like in pure supergravity from 11 dimensions and go down to dimension 3. Maybe I do it like this, sorry. And but instead of, so in the case of maximal supergravity, it's a split form, so it's the same. But in the case of supergravity theories of physics, you don't get the split forms or the maximally non-compact forms of the three-dimensional algebras. And as a result, the triangle is not a triangle, it's a bit convoluted. So you can see a line that's a U-duality line and so on. But here we took the ad hoc construction. We started from, again, the split forms of E8076 and so on in 3 dimensions, and tried to see how far we could go up or oxidize in less of dimensional reduction, this 3-dimensional theory to higher dimension. And to our surprise, we had done a systematic study, so it was just a matter of writing them in a column. This is the symmetric triangle. So it's another, a third triangle. And this triangle, I want to emphasize that it corresponds to, it contains a 3x3 imaginary square, but it's only simply laced. I can answer a question if you want to know how to make non-simply laced or partly non-simply laced, why in that part it is simply laced. And the rest contains non-simple factors R sometimes, and some ambiguities, so it's not a unique construction. And that's the thing we really want to understand. So I think I've been too long. I am 3 minutes late, sorry. The conclusion. So the first task I assigned myself was to classify occurrences of E8 and its cousins, or its brothers and sisters in each case. Then each family can be studied globally to exhibit common mechanisms and clarify or suppress the word magic, which I don't like. And then we have differentiated families, and they turn out to be differentiated by different properties. ADE is too broad. The number theoretical is probably exceptional, probably incomplete, not completely understood. The green construction is, as I said, was done using invariants. But the blue construction, the U-duality construction, is deeply using root systems. It's connected to algebraic geometry, to many things in Kähler-Einstein. So this is very important. But one family is connected to many physics problems. It's true for all. And the Palevey situation is, again, I described the ordinary differential equations, but to get contacts also with blue and green families, you can discretize the Palevey equations, and this they exist. Different polynomial equations exist. There are two types, or three types if I add the elliptic case. That additive and multiplicative. The multiplicative corresponds to the blue family, and the additive corresponds to the green family. This totally escapes me, and I skip many other instances of interesting things: anomalies, integrable superalgebras, the magic pyramid of Duff, and so on. Sorry for being late.
Okay, thank you. Thank you very much, Bernard. If there is one question, we can have a short question, or we can continue with the question in the break that is coming immediately. There is a question. Somebody want to ask a question? So if there is no question yet, we can go into the break, and then of course you can ask questions to all the speakers that spoke before. Thank you, Bernard.
Mauro has a question.
Mauro has a question, okay?
Oh, yes, it's a very, I guess, short and naive one, because you mentioned the concept of variance between different representations.
Yes.
Did I hear that correctly?
Yes.
Could you explain that to me, because I was not aware of that concept?
It's a bit long. For instance, I just don't remember all of them by heart, but they're all explained in the book by Cvitanovich of group theory. So I think it's available on the web. But for instance, for E7, so for E8, I think the E8 line at the bottom was not here, but so I lost my transposition. So in the green triangle, there is an E8 line, and this corresponds to adjoint representation, or powers of the adjoint representation, and the invariants are, I think, antisymmetric in the two power of adjoint and another condition. So they are very simple to explain, but a bit non-systematic, because for E7 you will need the antisymmetric tensor of the fundamental representation, etc., and the quartic.
Okay, so maybe I misheard, but I thought you said variance like in statistics or something, but it seems that you're talking about the invariance. Or
invariance, sorry, yes, I didn't hear. Invariance. So
okay.
Summarize. Each line, so what Cvitanovich calls E8 family, E7 family, and so on, is defined in a uniform way by some well-chosen set of invariants, and some fundamental representation to construct the algebra.
Okay, thanks.
Okay,
it's uniform in each line.
So then we'll start now the break, and we will meet again at 11, more or less in half an hour. But of course, you can continue the discussion with all the speakers that appeared before. Thank you very much, Bernard.